Okay. Hi, welcome back. Today we're talking about classification again, but this time we're talking about support vector machines. And so we're coming out of our theory discussion and talking about things that are a little bit more practical, but in this case, here the algorithms are motivated by really strong theory. Okay, so what we're going to talk about today are support vector machines, and so this, like naive Bayes and logistic regression, are a way of doing classification, and it's state-of-the-art. So if you're doing machine learning, you should know what support vector machines are, and you should be able to use them. And as I said before, they have nice theoretical properties, they work well, and the theory tells us that they should. Okay, so to talk about support vector machines, we need to think geometrically. So let's say that we have two classes, vacations and sports, that we want to classify. We have documents and we want to know, is this talking about sports or is it talking about vacations? And so let's say our training data look like this. We have 4 documents. Document 1 has ball, 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 travel. Document 2 has ball, ball. And vacations has travel, ball, travel, travel. Okay, so does the setup make sense?
Yeah.
Okay, all right. So let's try to think about this geometrically. What does this look like in a vector space? Okay, so let's think about document 1, which has ball 3 times and travel once. So where would that land in the vector space?
It will land 3, 1.
Okay, yeah. Okay, all right, sure. Okay, great. And so that's document 1. And how about document 2? Where would that land?
Document 2, there are 2 balls.
Yep.
And 0 travel.
Yep.
So it will land here.
Yep, that's right.
Yeah.
Okay, and now document 3 has 2 travels and 1 ball, so something like here. So let's make this an X instead. And then document 4 just has 1 travel here. So the reason that we went through this exercise is that we want to think about classifiers as geometric objects. And so what...
like how to put samples into a space.
Yeah, exactly. And our classifier is going to divide those 2 spaces.
Yeah.
So we can think about a classifier as some sort of line separating our 2 classes. And so this is what support vector machines do, and as it turns out, so does naive Bayes and logistic regression. They do the same thing, but support vector machines are motivated using this geometric intuition. Okay, so a little bit more technically what we just talked about. In this setup, each document is a vector. There is 1 dimension or 1 component for every term. And the terms are the axes. So each word is its own dimension. And because of this, it's really high dimensionality. So tens of thousands of dimensions, perhaps even more. So the question is, how do we do classification in this space? So any questions on the setup of vector spaces?
Not yet.
Okay, all right. The way that we do classification is we assume that documents are some sort of contiguous region. So if we have some space, you'll have class 1 over here, class 2 over here, and they'll be separated somehow. And that's the second assumption. And so what we want to do is we want to find some surface to divide these 2 regions.
Yeah. Okay.
All right, so just to put this intuition a little bit more, let's say that we're classifying documents still, and we have these 3 classes, China, Kenya, and the UK, and we want to classify this test document here. So where should it go, China, UK, or Kenya? We can draw lines between them, and the way that we draw the lines decides whether this document will be about China or about the UK. We could have just as easily drawn the line that way. Okay? Yeah, so, and the question for today is how do we draw these lines? All right, so first let's talk about a general class of classifiers called linear classifiers. And so in a linear classifier, you have some combination or weighted sum of your weights and your data. So this should look a lot like logistic regression. So in logistic regression, these were found using stochastic gradient descent or something like that. And the classification decision is, are these dot products greater than some threshold? And in logistic regression, this was the bias. For naive Bayes, this was the prior probability of the class. So there are many ways of finding the separator. We've done these two already. And so today, we're doing support vector machines. And in all of these cases, they assume that the data are linearly separable, that you can draw a line between the classes.
Yeah, and a plan maybe.
Yes, exactly. So let's. That's exactly right. So let's. So you answered this question already.
Yeah.
So that's the geometric intuition, that you want to have a plane separating these guys. So let's see what that looks like. So a linear classifier, if you just have one dimension, is what?
Is a dot.
Yeah, it's a point. So one class is to the left of the point, and one class is to the right. Okay, that's fairly simple. So now let's do 2 dimensions. And so what is a separator in 2 dimensions?
It's a line.
Yeah, exactly. And so you can have things above the line and things below the line. And in both cases, now we have 2 dimensions, so now we have 2 terms in our dot product. And let's just do one more dimension. So in 3 dimensions, what does a separator look like?
A plane.
Yeah, a plane. So you have things above the plane and things below the plane. And here you have 3 terms in your dot product. And you can keep going. Our computer hardware doesn't really support going any further, but these are now called hyperplanes as you go to higher dimensions. And you can have arbitrary terms in these products. So going up to tens of thousands of dimensions. Okay?
Okay.
All right. So let's review how naive Bayes and logistic regression are also linear classifiers. So for naive Bayes, our bias term, or our threshold, is the ratio of the background probabilities or the prior probabilities. And then our terms that we use in the dot product are the probability of a term in a class given the class and the probability of the term in the other class. And so this is exactly the same linear classifiers that we were working through here, formulated in naive Bayes. Yep. Okay?
Yeah.
All right, and logistic regression is the same thing, and the only difference is that we put it through this logistic function, and that's just to turn it into a probability. But the decision, whether it's in a class or not, is still the same thing. Okay, so the takeaway here is that we have 1, 2, 3 linear methods, but how are they different? They're different in the way that you choose what these betas are and what the linear separators look like. All right, any questions on the setup about what linear classifiers are?
No, it's pretty clear.
Okay, all right. Yeah, and so the question is, we have many ways of drawing hyperplanes. And so if this is class 1 and this is class 2, there are infinitely many hyperplanes that we could use to divide these classes, and in fact an uncountable number of planes that could divide these classes. How do we choose which one? And in many cases they will all separate the training set perfectly, and so they all get 0 training error. So how do you choose which one? And you don't know a priori how they'll do on test data, but presumably you want one that will do well on test data. Okay, so this is the intuition of support vector machines. Does the setup make sense about the question of how you choose a hyperplane?
Yeah.
Okay, all right. So let's see what support vector machines decide to do when they choose a hyperplane. So, just a little bit of background. Support vector machines have been really popular in the last, this is really 3 decades at this point. They've been applied, in many cases, it's really sort of a bread and butter algorithm at this point. And so the intuition behind support vector machines is that you want to find your decision boundary that is maximally far away from any of your training data. So this is the intuition, and we'll see why it's sort of intuitively good, and we'll also see why it's good theoretically. Okay, so let's say that we have data that look like this, and in 2 dimensions, a decision boundary is just a line. And so what we want to do is we want to maximize what's called the margin. And so the margin is the minimum distance from a point to the boundary. So this is called the margin here. And so you also have a margin here. And so here you're sort of defining a neutral zone between the 2 points, and you want the line to be maximally far away from both, say, the positive class and, say, the negative class. So does that make sense?
Yeah, makes sense.
Okay. So the reason that SVMs are called support vector machines is that these guys, the points that are the distance rho to the margin, are called support vectors. They're defining the fence posts that define this neutral zone between these 2 classes.
Yes.
And so in some sense, these are the hardest examples because they are the
Closest points to the plane.
Yeah, exactly. And they're the closest points to the plane, but also they're also the closest points to the enemy territory. And so these documents, if you're doing document classification, look the most like each other, and you want to find a decision boundary that keeps these guys as far apart as possible. So to think about it another way is that this is giving you a safety margin, and you could also choose a decision boundary that lies over here. So this would also get 0 training error. So why would this be a bad line to choose?
That is because maybe some points will land here, and in this way it will count as a counter.
Yeah, so you might have a positive point that's here, but because it's on the other side of the line, it'll be classified as negative.
Yeah.
But it's actually closer to these guys.
Yes.
And so another nice benefit, in addition to this being a large margin around the decision boundary, is that this also leads to planes that are really efficient in terms of memory usage, because you only have to care about the hard cases, the support vectors.
Yeah, we only need the support vectors to calculate the plane.
Exactly. So all of the other data you can throw away. It's just the hard cases, the support vectors, that you need to worry about.
Yeah, that makes sense.
Okay, so that's the intuition. So now let's go to the way that we talk about support vectors. So we'll change up notation a little bit. So we're moving away from the standard notation that logistic regression uses to the standard notation that support vector machines uses. So our betas are being replaced by W's, and our beta naught is being replaced by a B. But it's still the same thing. It's just, this is how support vector machine people write their equations. So this is how you define a hyperplane. One thing you need to watch out for is that some people use a plus here, some people use a minus here. So you need to keep track of which convention people are using. Okay, so the distance of a point to the hyperplane is defined by this. So here you have the dot product between the data and the weight vector plus the bias. And so then you divide by the norm of the weight vector to get the distance to the hyperplane. So if you have some point xi, you take the vector xi, which when we write it this way, it's the normal vector to the decision boundary. You take the dot product of these two guys and then divide by w. And hopefully you remember cosines enough to remember that. Okay, so then the margin is going to be those points for which this is going to be exactly 1. So does that make sense?
Why does it become 1?
Right, so it becomes 1 because we define the length of the vector w to be our margin.
Yeah.
So notice that this is a defined as, not an equal sign.
Yeah.
Okay. So this wouldn't be true for arbitrary w, but the smaller w is, the more confident we are. And for any point on the marginal hyperplane, then you get this nice equation that this is going to be plus minus 1. And so things that are not on the marginal hyperplane but are really confident are going to be larger values in absolute terms. So just to draw this again, we have plus 1 on this side, minus 1 on this side, and points over here can be like 5,000 when you take wx plus b.
Yes.
Okay, any questions?
No questions for me.
Okay, all right. Okay, so now that we formulated it this way, the problem of solving support vector machines is to find some vector that maximizes this, that maximizes our margin, or equivalently minimizes this quantity.
Yes. Why would we have the square here?
Right. So you don't necessarily need to have that here, but that's the convention, to have the 2 norm. You could also have the 1 norm. You could have other norms here.
Yeah, maybe it's easier for the calculation.
I guess a little bit. So this has a nicer derivative than the 1 norm. And so that's a good question. I don't know the answer to that. But this is the convention. Let me actually write that down so I remember to deal with that. Okay. Okay, so this is an optimization, so we want this value to be as small as possible, but we have constraints, and so we want all of these classification terms to be greater than or equal to 1. Yeah. So why is this not an absolute value term?
That is because the yi here is also, it already has a sign. Yeah, for the positive, it's 1, and this is bigger than 1, so it's, it's the same sign. So.
Exactly. Yeah. So that means we have no errors, and so if we had errors, this would be negative. So we don't want any errors whatsoever, on our training set at least. And for all of the points, we want them to be on the margin, on the marginal hyperplane. Okay, so next time we'll talk about the algorithm on how you find this. Okay, but in the meantime, let's talk about the theoretical guarantees of this algorithm. Okay, so there are 3 ways we can talk about the theoretical properties of SVMs. We can do leave one out error, VC dimension, and margin analysis. We'll briefly talk about all of them. Okay, so leave one out error is defined as the error by having a fairly odd setup. You use every point except 1 as your training set, and then you only have 1 point in your test set. Yeah. And then you average over all of them. So does the setup make sense?
Yeah, makes sense.
Okay, so that's what this notation means here, that we're going to classify just on a single point point I and see whether we're right or not. And so we have this test set of size 1, and we do this m times for each point in our data set, and then we see what our average error is. And so it's not too hard to see that this is an unbiased estimate of the generalization error because you are using it as a test set. This gives us some notion of how well we'll do on test data. So the interesting thing about support vector machines is that we only care about things that are support vectors. And so if something is not a support vector and we take it out of our training set, it doesn't affect our computation because it doesn't change the margin. If it's away from the margin and you leave it out, nothing bad will happen if you then rerun your algorithm. And so that means that when we're trying to figure out whether for some point, whether we get it wrong when we have leave one out error, there are two cases to consider. If it's a support vector, then bad things could happen. The margins could fall apart and we could be completely wrong. So we could, everything could go up in smoke. But if it's not a support vector, nothing happens. And then the answer doesn't change. And so in that case, if there are this many support vectors, then that's how many errors you have in this analysis. So if your data are nice and separable and you have a big margin with not a lot of support vectors, you're going to have relatively low error. So that's nice. Yeah. And this is actually something that we see in practice, that for many data sets you have few support vectors on the order of 10% or so, and so that's relatively good error. Okay, so the other argument that we can use is VC dimension. And so we had a discussion about VC dimensions. We can plug in d-dimensional hyperplanes into our VC dimension, which we worked through in class. And unfortunately, this is relatively useless when d is very large. And so here we're saying that the generalization error is going to be less than or equal to our empirical error plus some term that depends on the dimension. But when the dimension is tens of thousands, like for text, this is basically saying that your error will be less than, say, 200%, which isn't saying much. Any algorithm will have error of less than 200%. So that's not too useful. If you have a very small dimensional problem, this might be useful. However, one nice thing that Vapnik came up with is that if you consider the margin loss, so here we're going to define for a point a loss function. And so if x is greater than or equal to rho, your loss is 0. If it's in the margin, it's going to be 1 minus x over rho. And then if it's on the other side, then you're wrong, and so that's your loss. And so it looks something like this. So if you have x on this axis, 0 here, rho here, we're basically, oops, wrong way. We have 1 if we're less than 0, and then we work our way down to 0. And so you can think about this as a dot product of wx plus b, and how bad is it? And so if it's a really big number, then that's great. And if it's a negative number, that's not so good. Okay, so one thing that we can do is we can compute the empirical margin loss of a hypothesis in these terms. So we take this phi function, we plug in wx plus b, multiply by y, so that positive numbers are good, negative numbers are bad, and things in the margin are iffy. And so what you can prove is that the empirical margin loss of a hypothesis is going to be this, and then the points in the training sample that have been misclassified or classified with confidence less than p gives you a good estimate of your eventual generalization error based on this factor. And this factor includes this capital lambda term that basically says how big of a geometric space do your data take up. And so if your data live in some relatively constrained area and they're well separated, then you're going to do relatively well on your classification. And this is the intuition that leads to support vector machines performing well. Okay, any questions?
No questions.
Okay, all right, so so that's the good part of this. The bad part of this is that it's data dependent. It actually depends on what your data are. And so thus far we're talking about mostly data independent learning bounds, but this actually depends on what your data are. And so you need to look at your data first before you know how well you're going to do. But in practice, many data do have good margin properties. And if they have these good margin properties, SVMs work well. Yep. Okay, so to wrap up, how do you know what classifier to use? We talked about a number of classifiers. We talked about naive Bayes, logistic regression, and now support vector machines. How do you know which classifier to use? And so one question you might ask is, how much data are there? And so if you have no data, then you have to do something else. You can't use a classifier. You need to write regular expressions or use active learning or something like that. If you don't have very much data, naive Bayes is often a good choice because of the priors and the assumptions it makes about distributions, works relatively well. If you have a fair amount, then support vector machines are a good thing to use. They tend to have good accuracy and don't take too long to run. If you have just ginormous amounts of data, it really doesn't matter. Use whatever works. They'll basically get to the same decision, and really the quality of your features, which we talked about in the feature engineering lecture, matter quite a bit more. And so oftentimes, logistic regression or naive Bayes tends to scale a little bit better, and maybe logistic regression still works a little bit better, so you use that. But if you have a fancy pants support vector machines algorithm, and it still works on your huge data, then why not use that? Okay, any questions on what we talked about today?
No.
Okay, all right, so what are we talking about next? So one thing that we've been assuming through all of today is that our data are linearly separable. But what if our data look like this, where you have a positive class here, and then you also have an exclave of positive data that look like this, surrounded by negative data? How the heck can you classify this? You can't use a line to separate these two because these guys are all on the wrong side of the line. So we'll talk about two things. We'll talk about slack variables, where your data don't live on a perfect line, and we'll talk about kernels that allow you to have different geometries, not just linear.